Okay, perfect. And I share my screen. Good. Okay. I started the recording. If we make the break with the presentations, of course, I will stop recording. So you will have probably 2 videos for today's lecture, which is not a problem. I just wanted to let you know. Furthermore, just to make a summary, I apologize for the cancellation of the visit at the Chiusa di Casalecchio. Unfortunately, you know, the weather was very bad, and we don't have other opportunities to make the visit before Thursday next week. So they proposed to me June 1st, but I thought it's too late. So my proposed calendar for this week and the coming one is this week I'm lecturing today, just today, because on Thursday, you know that we cannot teach every Thursday, and also on Thursday this week I am busy. Next week I will teach 3 hours on Monday, again on decision theory, and probably it will be decision theory, the last topic I am teaching for this course. So maybe that I am removing a couple of links from our web page where you can find the tutorials. At the end of the course, I will leave on the web page only the links that you have to use, unless I put a note, okay? And so next week I'm teaching on Monday again, and I will close on Thursday, May 21st, with probably 1 hour lecturing and conversation to make a summary, and 1 hour visit at the lab of hydraulics here in the university. We go by feet, it's just close by. And the visit at the lab, I think it is interesting. It is related more to fluid dynamics and not really to climate change adaptation, but we will see small-scale physical models that are often used to test design projects in ocean engineering and fluvial hydraulics, which means that these design projects, being related to coastal engineering and river engineering, may be related to climate change adaptation, of course, but the relationship is not a direct relationship. On the other hand, you know that when it turns into practice, climate change adaptation means design projects or means policies. So the relationship is not direct, but of course, it's a direct relationship with water engineering, which has in turn a direct relationship with climate change adaptation. Anyway, I think it's an interesting visit. It's a nice way of closing our cooperation in terms of lecturing. And then, of course, we will continue to cooperate with the exam. As I said, after the visit to the lab, I will be pleased to invite you at the bar for a coffee, and then to say goodbye for now. Okay, now decision theory. We started, and I have a PowerPoint presentation, as you know, which we already started viewing. It has been updated during the last week, not for the parts that we already discussed, but for the parts that I am discussing today. We discussed about the importance of decision making. I want to stress it once more. It is extremely important because in climate change adaptation, we have to take decisions between several different alternatives. And we have several different scenarios for the future climate because climate predictions are uncertain. So it is a decision to be taken in the presence of uncertainty with several alternatives, several possible alternatives, including nature-based solutions, including design projects, hard structures, and therefore it's a complicated decision. And we will see why it is important that we use decision-making, in particular because climate change may also be an opportunity. And if we want to inspect these opportunities, if there are opportunities, it's our duty, it's our professional task and challenge to try to take advantage from them. And if there is uncertainty, in order to benefit from possible opportunities, we need a structured way of taking decisions in the presence of uncertainty. And this is what we call the decision theory. We already discussed about robust optimization. Robust optimization, it's a particular version of optimization where we look for the optimum in the presence of several scenarios for the future, and we look for the optimal solution. We discussed robust decision making. Robust decision making tends to lead to no regret decisions, and we said that robust decision making is based on identification of future scenarios, metrics to describe performances, and candidate strategies. There are also, when we talk about metrics, implicitly we also talk about models for estimating these metrics. We didn't discuss in detail what kind of metrics, what kind of models we could use. We just said robust decision-making looks at several alternatives with respect to several different scenarios and tries to minimize the regret. And we talked about the min-max method, or max-min, depending on the sign that you give to the damage benefit that you may get from a decision. I will give you an example now of min-max within the discussion of the next method that I want to discuss in detail, infogap. Infogap, I think it's a nice example, and this is why I decided to discuss it in detail, because infogap is different with respect to robust decision making, because it also looks for opportunities. It looks for opportunities given by uncertainty. Uncertainty, of course, gives possible damage. When you are not able to predict the future, you may have a bad outcome, but you may also have opportunities, as we will see. Because if we make a prediction, and the prediction is that in the future there is less water, but there is uncertainty, it means that in the future you may have also more water. And therefore, if this uncertainty translates in more water, it's an opportunity. And there might be decisions that allow me to profit from this possible, eventual opportunity. Okay? There are other decisions, other alternatives, which may not allow to profit from unexpected opportunities. Infogap looks at unexpected opportunities. Infogap can be considered a special case of robust decision making, but it's different. It's different because it doesn't look only at minimizing the regret. Infogap also looks at opportunities. And this is why I decided also to give an example. And so, as you see here in red, however, it recognizes that uncertainty may also be an opportunity. Okay? I always discuss of uncertainty in, let me say, negative terms, and this is what many people do. But uncertainty may be something that brings an opportunity. The fact that we become more resilient may be an opportunity. The fact that, as I said, we may profit from unexpected outcome. This unexpected outcome is also called windfall. Windfall, it's in Italian, to give you an idea to those of you who are Italians, windfall is manna dal cielo. Okay, so it's something that it's an unexpected benefit. The unexpected benefit, in English, we call it windfall. Okay. Okay, so, I mean, getting into the details of these methods, if you just talk of them in a narrative way, it's simple, like robust decision making. Robust decision making is simple if we limit ourselves to the narrative. Robust decision making minimizes the regret. It's very simple to explain. I choose the alternative minimizing the regret. But if you want to give an example, you have to also specify a model for evaluating the impact, for computing the benefit or computing the damage. Okay, damage is a benefit with the negative sign. Okay, so a model means that you have to introduce some math, and this is why today I am introducing some math. Okay, and because I want to get into the details. This makes the difference between a narrative and an operational phase. Okay. Okay. Let me see. Nothing more to say here. Okay. So let me just give an example of min-max, because InfoGap has many similarities with the min-max. A similarity, but has also many differences. Min-max is also called worst case analysis. It's a particular case of also of robust decision making. Robust decision making can converge to min-max, and also InfoGap, as we will see, may converge to min-max. Min-max looks for the minimization of the damage that we may get from a decision. So we want to take, we look for the max damage, and we take the minimum. So we look for the max damage associated to each decision. Okay, if I have two alternatives, I look for the max damage and I take the minimum. So let me give you an example. Suppose that we have two decisions, two alternatives. We have a decision between two alternatives, A and B. And we have two scenarios, so it's very simple. Again, my decision is alternative A or alternative B. And for the future climate, I have two scenarios, just two. Actually, in practice, we have several alternatives and several scenarios, but let me just make it very simple. And let's suppose that we evaluate the damage, okay? And we want to minimize the damage. So scenario one leads to the level of damage 5, with more damage associated to increasing value. So 5 is quite substantial damage, okay? Scenario alternative A with scenario 1 leads to a level of damage 5. Scenario 2, again with alternative A, leads to level of damage 1. So basically, if I select alternative A, I may have quite a reduced damage, 1, but if I get future climate 1, scenario 1, I have quite a big damage. So alternative A with the two climate scenarios gives, for one climate scenario, a huge damage, for the other climate scenario, quite a reduced damage. Alternative B, again, for the two scenarios, with scenario 1 leads to level of damage 4, and with scenario 2 leads to a level of damage 2. So I want to minimize the damage, and therefore min-max would select alternative B, because the worst case is level of damage 4. Alternative A has a worst case, and therefore I prefer B. So I am not considering that alternative A may lead to a lower damage with respect to alternative B if scenario 2 occurs. I'm just looking at the worst case, and I want to minimize the worst damage. So I select alternative B. I'm not looking for opportunities. It's quite simple, but requires some concentration, okay? Is this clear? Good. This is min-max. So InfoGap, as I said, looks for opportunity. So InfoGap, in this case, would say, but alternative A gives a damage 1. if scenario 2 occurs. So what should I select here? InfoGap tries to guide us in the evaluation of both min-max and the opportunity. And we assume that we don't have probability associated to these future scenarios. Because with the probability, it would be easier. If I knew that scenario 1 is 90% and scenario 2 is 10% probability, it's easier to make the decision. But climate change predictions actually don't tell us this. They just give us a lot of scenarios. They try to give probabilities, but we said that these probabilities are not really correct. So this is precisely our case. We have several scenarios for the future climate, but we don't have probabilities. Again, if you look at IPCC associate probabilities, but they don't call them probabilities. They call them level of confidence. Level of confidence. Because they don't use the word probability, because they know that it's not, strictly speaking, a probability. So beware of that. Our case is several future scenarios. We just look at their possibility. Are they possible? Yes. Okay. So let's consider them all together. Good. Now, there are many repetitions in these slides, okay? So if you look at the first bullet point, InfoGap recognizes that uncertainty implies not only possible worst outcomes, but also opportunities. There are many repetitions because I use repetition to stress the concept. In the context of climate change, the presence of uncertainty associated to a prediction leads to a possibly bad future, but it also implies that the future may be not so bad. So I have climate predictions. There is uncertainty. Uncertainty means that it could be worse than that, but it could be better. So we may eventually get a windfall. Okay. So I start giving an example here. Third bullet point. For instance, a prediction may depict a drier future in terms of water. Okay. And therefore less water available for irrigation. But the presence of uncertainty means that in the future I may have also more water available for irrigation. This is important to consider because if you look at climate change, why we think that the future will be drier? Because we think that with increased temperature means more dryness, of course, a drier future. But why? Because increased temperature means increased evaporation. So, I mean, increased evaporation means that I have less water into the rivers, less water into the reservoirs. But on the other hand, increased evaporation may mean more rainfall. More rainfall may mean more water available. And these feedbacks are not fully understood, as I said many times. So indeed, an increased temperature in some regions of the world, global warming, brought more rainfall, more water available for irrigation. And this is not, it's not uniform. It depends on many local behavior, local contexts. So again, I have a prediction which says that globally or locally, I may have less water available, but the presence of uncertainty means that I may have also more. So climate change not necessarily brings a disadvantage in terms of available water for irrigation. It may mean more. Maybe this is the reason why after, if you look at the Emilia-Romagna region or north of Italy, after 1950, we didn't get a very long drought. Maybe because the increased temperature may have implied more evaporation and therefore more rainfall. Who knows? We don't know that. But actually, the situation is that from 1950, while during the 19th century and the first part of the 20th century, we got a lot of droughts, but I mean very severe droughts that lasted like 5, 6 years. After 1950, we didn't get any. Okay, these long droughts are very rare. Maybe that now, even if it rained last week, maybe that now we are in a long drought. We don't know. But on the other hand, it is also possible that global warming decreased the frequency of droughts. Okay, we don't know that. By the way, if you want to get a nice story of this, maybe that I already mentioned this to you, but in my, just for your information, not for the exam, in my website, there is a ebook. If you go here on the left, a travel through time to explore past and future mega droughts. And it's an history of drought occurred in the past. And there is here a description of an interesting drought, not here, sorry, it's another page, just 1 second. It's 8 years ago. What is the title? The Dust Bowl. Okay. If you look on the web, there is a Wikipedia page on the Dust Bowl, which is linked here. It's very interesting. This occurred in the United States, in the prairies of the United States, from 1930 to 1936, and it caused a mass migration, and it lasted like 6 or 7 years, this drought. So if you want to get an example of droughts that occurred in the past, the Dust Bowl is a very nice example that you can find from my ebook again. Okay, this is a famous picture that was taken by a photographer and of people migrating. Okay, let's go back here. So again, it may be an opportunity, and InfoGap leads to identifying all possible future by evaluating what is the minimum requirement and what is the minimum requirement, for instance, in terms of water availability. What is the minimum required water to ensure a sustainable future? So instead of looking first to an estimate of uncertainty, and then once uncertainty is estimated, evaluating the possible outcomes, InfoGap takes the other way around, evaluates all the possible outcomes and identifies what is the max level of uncertainty which we need to make sure that the future is sustainable. Again, it's the other way around. Given that we don't know uncertainty, we look at all the possibilities, all the scenarios, and then by referring to a prediction like water resources availability, we estimate the max uncertainty compatible with a sustainable future. So in terms, for instance, of water for irrigation, I make a prediction, and then I estimate the max uncertainty associated to that prediction that makes irrigation sustainable. It's the other way around. It's a smart idea. So I estimate the max tolerable uncertainty. Okay. In narrative terms, I hope it's easy to be understood. But when you go to the application, it's not so easy, of course. Let's try to move into an application. I skipped the slide because I want to move to the applications quickly. So there are 3 essential components that I have to take into account and to involve in order to apply InfoGap. So a model that is serves to make the prediction, the climate model, for instance. Maybe if we talk about a prediction of water for irrigation, we need more than a climate model. We also need a hydrological model. If we talk about, wildfires, then we need a prediction of temperature, and then a model that gives to me the likelihood of fires depending on the increased temperature. Just to give you two different examples. So I need a prediction model in order to estimate the future. I need a performance requirement. So a model for estimating, I need to estimate the performance of the system. And I need to set the requirements. What is the minimum level of water, the minimum amount of water that I need to make sure that irrigation is sustainable? And then an uncertainty model. An uncertainty model means how to quantify the uncertainty of the prediction. So let's go to the example then, okay? So let's make an example that refers to what I called into play so far. So water for irrigation. I have a model that gives to me an estimate of future water available for irrigation. Let's call it with the symbol X, okay? Somewhere here, I hope that there is, yeah, X, water for irrigation. So we know an estimated value of water for irrigation because the climate models give us a best estimate. Very often, if we talk about water for irrigation, is lower than the current value because they are conservative and they give us not only a range of possibilities, they also give us a best estimate. And we can make a computation with reference to the best estimate. But if we only use the best estimate, we don't take uncertainty into account. But we have a best estimate. And the best estimate will be called in the next slide X tilde, with a tilde and over bar, with an over tilde. Okay. And then we know that the future reality may be represented by a deviation from the best estimate of X. And let's call this deviation with a plus minus S. S, lowercase s, is the error. So the future will be X plus minus S. S is an error. Okay. But X must be positive. Okay. So there are constraints. The prediction cannot tell me that the future water is minus 10. Okay, it must be positive. So X plus minus S with a constraint that X is greater or equal than 0 cannot be negative. Okay. We don't know a worst case or max error, and we have no probabilistic information. So just X plus minus S, X greater than 0, greater or equal than 0, but no probabilistic information. Good. Now, we assume that the benefit, so our performance, is given by this equation. It's very simple. Let me show you what is the behavior of this equation. So this is the benefit. So this is X. Suppose that it's millions of cubic meters, and this is the benefit, millions of euros. Okay, it's just arbitrary, but this is common in agriculture, water for irrigation. It means that if you start from 0 water, you have 0 benefit, of course. No water for irrigation, no agriculture in a irrigation fed agriculture. And then you have a rapid increase of the benefit for increasing water volume for irrigation. But this the concavity of the curve, it's the concavity, it's a concave curve with the concavity of the curve towards the bottom of the graph, because if you increase water availability, the gradient of the benefit decreases and you get to a max asymptotically. It's clear that we get to a max because once that we have enough water to fully feed the crop, if we give more water, we don't have more benefit. conversely, in some cases, if we give too much water, we have illness of the crops. But let's just focus on an asymptotic function, which tends to a max benefit. Max benefit, which is reached for a given amount of water. Okay. And mathematically, I go back. This is the shape. B0 is it's the value of the benefit for x equal to 0, which is, in this case is 0, and B1 is the max benefit. Okay, and we don't need to fix values here. Okay, we may make an exercise by fixing a value, but we don't need to fix it here. I just want to denote with the symbol B tilde and X tilde the benefit corresponding to the best estimate for the water volume. So the best estimate, as I told you before, is indicated by X tilde, and I have a benefit B tilde. So I have a best prediction of water for irrigation, X tilde, which gives a benefit B tilde. Is it clear? It's not indicated in the graph. I don't put here where is X tilde, maybe 10, maybe 15. Let's keep it completely arbitrary for now. But I hope it's clear that in this range of benefits, you may extend also here to 25 to 30, and in the range of X, there is a best estimate. Here I look at the possible values, and there is a best estimate in between. And this graph, as I said, could be extended because it's just limited here for the purpose of giving an example, but it can be extended. Now, let's introduce, 1 second. This is the performance model, okay? The mathematical relationship that you see here. Again, fully arbitrary. You may have different functions, especially if you consider a different example, okay? And this is the performance. Yeah, please.
Sorry.
Yeah.
How can I estimate a best?
Say again, please.
How can I estimate a best in water availability?
So you said how, sorry, I tried to repeat your question to make sure that I understood. The question was, how can I get the best estimate?
Yes, exactly.
Okay, the best estimate is given typically for water availability by a climate model, which gives you a best estimate for precipitation. And then you need, in cascade to the climate model, a hydrological model that transforms the estimate of precipitation into an estimate of water availability. Is it clear?
Okay, so is linked to a certain region, a certain, I don't know.
Yes, we need to refer to a specific case study, and like maybe Emilia-Romagna region, you have climate models that give to you, and you can find the data on the web, precipitation predictions in the future, and then you have to set up a hydrological model transforming for each basin precipitation prediction into runoff prediction. Is it clear?
Okay, so always also a climate model, so uncertainty again.
Yes, because any model brings uncertainty. So in this case, you have a cascade of uncertainties. It is particularly complicated to estimate it, but we are not estimating uncertainty here. We are just looking at the possible uncertainty. Correct? Or do you need more? Okay.
No, only the concept of best is not so clear to me, but maybe.
Yeah, I can explain. So when you consider, for instance, climate predictions, let's limit to climate predictions. You have several scenarios, and then usually IPCC or any provider of scenarios tries to identify the most likely, and usually what they do is to compute the average, because they want to give you a best guess. Why they want to give you a best guess? Because of course, if they give to you the full range of scenarios, especially for communication, it's not clear what the effect of climate change will be. So they try to identify a best one. On the other hand, best means the one that I believe more will be the reality. On the other hand, this best is not rigorously estimated. So if you just compute the average, of course, it's not a rigorous estimation. And this is why we have uncertainty. So this is why we admit the presence of uncertainty.
Okay, thank you.
Okay. And of course, we are not here going into the detail of a specific catchment. Last Monday, we had one presentation who presented a hydrological model, and you got the feeling of what would be a specific application. We don't get into the details of a specific application because it would require a lot of time to be developed in detail. But what I am referring to here is very generic. I mean, it's you have always a best estimate for a prediction, but there is associated an uncertainty which cannot be rigorously quantified. Okay, so it's clear that it's may look like a smart solution to estimate the average. I have several scenarios, I take the average as the best estimate. On the other hand, you cannot say this is the truth. It is just the best prediction, the one that I trust more with a subjective evaluation. But on the other hand, it's not the reality for sure. Okay. As I said, we have uncertainty, and then let's quantify the uncertainty. The uncertainty, we introduced uncertainty with an error term, S. You see at the denominator here, an error term. I said X plus minus S. So let's quantify uncertainty in a relative manner. So let's quantify uncertainty by taking the difference between a generic prediction X minus what I identified as the best estimate. Okay, so if the best estimate becomes true, then the numerator, this difference is 0. If the best estimate x tilde becomes the truth, then the numerator, the difference x minus x tilde is 0. Instead, if there is an error in the future, the reality is different. The reality x is different by x tilde, different from x tilde, then the difference is a number which may be positive or negative, but I'm taking the absolute value here, okay? So the difference is a number. And if I divide the difference between I divide it by S, which is my error, the tolerable error, the estimated error, then I get a relative measurement of uncertainty. Okay. And I impose that this difference is less than H, which is generic. It's generic, okay? So let me just summarize this step here. I admit that there is a prediction error S. I take the generic, I fix that S is like in water resources availability is an assigned volume of water. So my prediction is X plus minus S. And if I divide the difference between what becomes true and the best estimate, I divide it by S, and I impose that this is less or equal than a value H. So if the best estimate becomes true, as you see, H is 0, independently of what I fixed, the S value that I fixed. If I have a future that is different from the best estimate, I have an increasing value of H. Okay. And so in this way, H becomes an index that quantifies uncertainty. It is subjective because it depends on the level of S that I fixed at the beginning. But just take into account that it's quite frequent that climate models give you a range of scenarios, and you may take the average as X tilde, and then you can take the width of this scenario as S value. Okay, so let me just make a graph on the blackboard and give you a more detailed representation. Let me change, just 1 second, I just share the screen because I want to make the blackboard more visible. And I need to change the camera. Let me see. Okay, perfect. So let's suppose that you have this future with, so you have, this is 2023, and this is 2100. Okay, let me see if it is in the blackboard. Yes, okay. This is 2100, and this is 2023. And then this is X, our X, water resources availability. And you have several different climate scenarios. Typically, they start from, of course, the observed value at 2023, and then they give in the future a prediction like this one, okay? And then you may have also something increasing here, okay? Usually you find predictions that are not increasing because climate models are conservative, but we can also make an example like this. So if you want a prediction to 2100, so this is the average, is the best. This is X tilde, okay? And then you can estimate S in this way. This is something like, let's see, 2S. So you estimate uncertainty just by looking at the width of the prediction. But then in the future, you may have, so this one is X tilde plus S, and this one is X tilde minus S, okay? So let's, but in the future, you may have the reality, which is this one. This is my X. And then you compute X minus X tilde divided by this, and this is my H. And or estimated, let me see how the symbol of this in the slide. Just 1 second. Okay. This is, let's call it H star, because this is the actual age, okay, which materializes into the future. I hope it's clear. Yeah, a question from the room.
Yeah, so X without tilde, it's the actual value in the future.
Yeah,
it's 14% in reality.
Yeah.
How do we right now in 2023 we make a prediction? How can we do the calculation with the age now?
The calculation of the age is something that you do, you fix. So let me just share the screen. Because the question is, how can I compute age now? So what is, in other words, if I reformulate the question, how can I estimate the future value of X? This is your question, okay? The future true value of X, okay? Typically, you set a critical value of X, and you say, basically, I can't, in order to ensure sustainability, I can't sustain a value of X lower than, say, XC, critical value. And then you put into the equation that you see on the screen, the critical value here, and you impose that uncertainty, H is a quantification of the true uncertainty, is lower than the value of H that corresponds to XC. Is it clear? So when I have a climate prediction, I have indeed an estimate of uncertainty, which is given by S. It's the width of the various scenarios. If you are in the room, you can see it on the blackboard, okay? This is an estimate of uncertainty, which is not, as we say, correct. So the future may go out of this range of uncertainty. Okay, and therefore I estimate what is the critical value of X, and I fix the max distance of the true value in the future from what is predicted to ensure sustainability. This is the condition that I impose. When I impose an upper value of H, it means that I am fixing how much the future true value of water resources availability can depart from the predictions, including uncertainty S. Okay, so I have an uncertain prediction of the future. The reality may depart from this uncertain prediction. How much? H. H is the max level of uncertainty that I can tolerate to ensure sustainability. In fact, here you see, sorry, the lower equation. Lower equation which says that in mathematical terms, what I just said. So I have a critical value of the benefit BC, which corresponds to a critical value of water availability in the future, XC. How to estimate this critical value of benefit through this function here? Okay, so basically through this function, I set the mean benefit, which I can tolerate in the future, which corresponds to a minimum water available for irrigation. And then I look for the uncertainty, the max uncertainty that gives to me this minimum benefit. Look, max H. I'm looking for the max H with minimum benefit for all the scenarios greater than the critical value. So I am looking for the max uncertainty, the max H value. The max uncertainty means the max true uncertainty, the max error in the prediction, which allows me to anyway get the minimum benefit. I look for the maximum uncertainty to ensure sustainability. Okay, and I want to express it in mathematical terms. In the web pages, there are more details. Still, the web page is something that I have just written a couple of months ago. If you see something that is not clear, just let me know. Okay, you have still 1 month to go before the exam. And I can translate, I can depict this function. This function is called the robustness function, and this is the robustness function. So you see here, basically, this function gives to you on the ordinates h, okay, and it's the h that corresponds to a given critical benefit, and here there is a mistake. I need to change this. It's not benefit xc, but it's benefit corresponding to xc. This one, I need to correct this. I'm sorry, I just see this now. It's benefit corresponding to xc. Okay. Because the benefit is called b. So here I should have put here BC. Now, but let's try to elaborate the interpretation of this figure because it's not difficult. Here you see, just look at the horizontal axis as the critical benefit. And let's suppose that you want a critical benefit that is very high, like 24 here. The critical benefit, if it is very high, it must correspond to a limited value of uncertainty, correct? Because if you fix a critical benefit that is very ambitious, then you need a low uncertainty to get it. So basically here you have for decreasing uncertainty, you have an increasing value of the critical benefit. Conversely, if your critical benefit is very low, like 5 million euros, you can tolerate a very large uncertainty. Of course, bigger is better here. Bigger uncertainty is better for us. Bigger uncertainty means that the method is very robust. Because here, if I had like for a benefit of 20, I have an uncertainty of 0.6, which means a relative error in the estimate of a relative error with respect to my predictions, my uncertainty of the predictions of 0.6. I would prefer to have a larger uncertainty here, because if my critical benefit is 20, if I want to get in the worst case 20, I would prefer that I'm allowed much more uncertainty, okay, with respect to the predictions. Because even if the prediction don't become true, I get my critical benefit anyway. Instead, if I have a low uncertainty, it means that I need true predictions in order to get the critical benefit, which is not a nice, because if I don't trust the model, I mean, I make my best selection of the alternative, I make my best decision basing on the model estimate. And clearly, if I don't trust the model, I would prefer that I am allowed much more model uncertainty in the prediction rather than being told that in order to get my critical benefit, I need the model to be very precise. So bigger is better. In this case, I have this function, okay, but I would have preferred something like steeper, okay, so something like going up with a steeper pattern, because it means more, I am granted the possibility of getting more uncertainty. And this is called the robustness function. And here you see that typically we have what is called the zeroing property. It means that typically we have a value of the performance, in this case the benefit, that corresponds to zero uncertainty, which corresponds to our best estimate. The zero uncertainty means best estimate. So typically we have best estimate for the benefit, which corresponds to zero uncertainty, which corresponds to the best estimated prediction. And this is what we think is the max that we can take. So I take the model, I have my prediction, my best prediction. I make my decision based on the best prediction. And typically I take my decision so that in absence of uncertainty, in correspondence of the best prediction, I get the max benefit. Okay. So the zeroing properties means that for zero uncertainty, I get the benefits corresponding to the best prediction. Of course, now you could say, but if I get more water than the best prediction, this is not evaluated here. Here we look only at the solutions that give the benefit greater than the critical value. So this robustness function doesn't evaluate the opportunity. It only tells me what is the max level of uncertainty that I can tolerate, still performing in a satisfactory manner. Okay, now I suggest that we stop here and we give the word to you for the presentations. I mean, as I said, this is not easy. I understand it's not easy, so it needs some elaboration on your side, okay? And the example that I provided, I think it's a good guidance. I have also a reference on the web that is open source. I'm not sure if I linked it. Just one second, I check. If not, I can. But I think it's not easier with respect to this presentation. So I'm not sure I should suggest it to you. My suggestion is to work on these tutorials because I tried to simplify things. Let me see, decision theory, and let me see if I linked in the references. I think, yeah. I think it is this one. Just one second. No, it's not this one. Let me see. Yeah, it is this one. Basically, there is this PDF. It's a book which is available on the web, and there is